Hi everyone. In section 2.4, we found complex zeros for quadratic functions. Now in section 2.5, we're going to find complex zeros for higher degree polynomial functions. For now, we'll typically assume that f of x is a non-constant polynomial with real coefficients and written in descending powers. We'll go straight to an example we saw back in 2.3. Factor f of x, which is 4x cubed minus 5x squared minus 7x plus 2. And by factor, we mean factor completely. That's assumed. And we're going to find all of its real zeros. Now, first of all, notice that the GCF is 1. If the GCF were something different, factor it out. Now, you see this polynomial, and it has 4 terms. So you might consider something like factoring by grouping if you're lucky, but it does not appear that factoring by grouping will help us much. So we're going to resort to using the rational zero test, or the rational roots theorem, which is the theorem our little bird used back in section 2.3. Remember, we saw this problem before in section 2.3. But we needed the help of a little bird who had taken pre-calculus. This bird came into the room and whispered to us, tweet, tweet, hey, I think 2 is a 0 for this function. And then that helped to unlock the first door. It was the first key, and then we proceeded to factor f of x. But how did the bird know that 2 was a 0? Well, the bird was hoping that teacher was being nice, and that at least one of the zeros for this thing would be a rational number, which is why the rational zero test, or rational roots theorem, was being applied. So you're hoping that teacher is nice, and that at least one of the zeros here will be a rational number. Now, it would be really helpful if we could get a nice finite list of possible rational zeros. If this thing has a rational zero, what could it be? Is there a finite list that we could choose from? The rational zero test does exactly that. It allows us to list the candidates for the possible rational zeros of f. So here's how we apply the rational zero test, and then we'll discuss the theorem in general later on. So we focus on 2 key terms here. Once again, the constant term and the leading term. The constant term is 2 here. The leading term is 4x cubed. And really, we just have to focus on the leading coefficient, which is 4 here. So we're going to focus on the constant term and the leading coefficient. The constant term is 2. And we're going to call the factors of the constant term, or the divisors of the constant term, the possible values for p. Now don't worry about the way we label these factors, p and q. The main thing is we're going to consider the factors of the constant term here, and then later on, the factors of the leading coefficient over here, which will be the possible values for q. So the factors of the constant term are given by plus or minus 1 and plus or minus 2. The plus or minus symbols are important. Remember that the negative values are also possible. So the factors of the constant term 2 are plus or minus 1 and plus or minus 2. The factors of the leading coefficient 4 are plus or minus 1, plus or minus 2, and plus or minus 4. Now, the bottom line is that we're going to have, as our list of possible rational zeros, the candidates that we can get from this form. Now, some students might put a big old plus or minus in front. That's okay if you remember to keep putting it in. Otherwise, it might be safer to keep putting in the plus or minus symbols. The bottom line is that we need to have, in our format, factors of the constant term over factors of leading coefficient. The possible values of p over the possible values of q. So the factors of the constant term, plus or minus 1 and plus or minus 2, over the factors of the leading coefficient, plus or minus 1, plus or minus 2, and plus or minus 4. Again, you can think of this as a template that you can work off of. Never give this as your final answer, but this is a template that you can work off of. So let's get the various combinations we can get here. The various possible values of the numerator over the various possible values of the denominator. Let's start with the possible candidates with plus or minus 1 on top. So we get plus or minus 1, and then plus or minus 1 over 1 first, then plus or minus 1 over 2, and then plus or minus 1 over 4. So these three pairs of possibilities with plus or minus 1 on the top. And then consider the possibilities with plus or minus 2 on top. We have plus or minus 2 over plus or minus 1, plus or minus 2 over plus or minus 2, and plus or minus 2 over plus or minus 4. And then we simplify these fractions. So our simplified list of candidates will be plus or minus 1, plus or minus 1/2, plus or minus 1/4, plus or minus 2. Here we get plus or minus 1 again, but that's redundant. We already have plus or minus 1 over here. We don't need it again. And then plus or minus 2 over 4. Again, that's plus or minus 1/2, which is redundant. We don't need to list those again. So this is our list. Our list of candidates for possible rational zeros or roots of f. So if f here has a rational zero, it must be in this list. In particular, there's no way that 3 or 4 or negative 7/3 or something like that could be a rational zero, because those numbers are not in this list. Of course, not all 8 of these could be zeros, because it's only a third degree polynomial. It can have at most 3 zeros. But if it does have a rational zero, it's got to be in this list. As it turns out, this has 3 zeros, and they're all rational, and they're all in this list. Now, before we go further, I need to talk about how to generalize this. What theorem leads to this list of candidates? That's next.